Okay, people. It is Saturday morning, and we're going to do part 2 of the Treemap Viewer that I started last night as a weekend project. Now, this is intended to be code for generally viewing any kind of tree map that we give out with the compiler, maybe as a way of starting a data visualization module that will have a lot of other stuff eventually, someday. Now, also the reason that I wanted it is to help with program visualization as a shorter term specific goal. But for some reason, and I'm not sure why I did this in retrospect, but for some reason, when I started making the code, I decided to sort of bootstrap it with data and maybe an example program from a file system data, right? Because you want hierarchical data for a tree map. So last night, we made this program. It's just a copy of the SIMP sample program so far, except when you start it up, it loads a hard-coded folder and recursively traverses it and gets the sizes of all the files and puts those in a tree map. And then it builds a hierarchical size representation, which all the way up to the root. And you can see that happen in part 1, if you would like. By the way, you'll notice when I was alt-tabbing how frickin' pompous Microsoft is. This popped up, this OneNote window. I don't know if I accidentally hit a hotkey that launched it, or if it was like on a timer from 2 weeks from starting the laptop. I don't know. There's no close button on this window. Okay. Also, there is a title bar that you can use it, move it around, but it's completely invisible. If I click here, that's in the title bar. If I click here, that's not. Oh, there's a hidden iconify button somewhere here, but it won't close. Oh, wait. No, that launched OneNote anyway. No, I'm not going to accept. They're such assholes. By the way, Windows also, yesterday, before the part 1 stream, it updated and restarted my laptop again without asking, right, just overnight. And I realize they've done that a few times in a row now again. And it's funny because they were, for a little bit, they were asking again before restarting. And now they just don't bother to ask again. And I wonder if this is a thing at Microsoft where there's like, they know that everybody hates this and they get all sorts of complaints about it. So like every couple of years, some manager at Microsoft goes like, we have to fix this. Everybody hates it. So they turn back on the box that asks before updating. And then as soon as they do that, their metrics on how many people update to the new version of Windows probably like plummet, just goes off a cliff, and everybody there panics. And they're like, oh my God, we have to turn back on the stealth auto updates because otherwise nobody fucking wants the newest version of Windows, which is obvious. Nobody wants to update Windows because you never get anything for it. It's always stupid nothing that you don't care about, and it always restarts your machine, and sometimes it's a very long, painful process. So why do you guys do it so often? Anyway, that's all off topic. We're going to program. Okay, so we are now we have this file Treemap, which will probably move into a module, that builds a Treemap data structure. It's pretty simple. It's only 80 lines so far. Our next step is to put this on the screen. Okay, so the first thing we're going to do is just draw a frickin' rectangle on the screen in the place where we want our tree map to go. Then we'll go and start making a tree map visualization or visual data structure update routine. So the way that we authored this file, there's two structures, right? There's tree map and tree map display. Tree map display isn't even real yet. This has no code that does anything with it. Right now we just set this up, which is the source data, right? That has sizes attached to a hierarchical representation, right? You have a name and a size for every node. So the idea is this stays mostly static. You could update it, you could refresh it, or you could even update it incrementally by changing the size of a child node or adding or deleting a child node. We don't support those right now because we don't care yet, if ever. But keeping this static and refreshing the display is a much faster operation probably, and you probably want to do that all the time. We will illustrate actually, hopefully today, we'll see. Anyway, so we'll start writing the thing that generates this, and the goal, we want to do a squarified tree map, which you could search for the paper about that, like I said, should be like a 1-paragraph paper. Although I'm realizing I don't totally remember what the point of the paper was. We'll get to that. But it's a way of allocating nodes so that they're roughly square, right? But we don't even need to do that to get things on the screen. So just to get things on the screen, we could do a more naive tree map that has horribly shaped rectangles, and that's fine, right? And we can make that work, and then we can do the squarified part. So that's my goal for right now, is to just get the tree map on the screen, right? It's like putting the lotion in the basket, but it's different. How is it different to a quad tree? A quad tree is a totally different thing. Totally different. You can watch part 1. In the beginning of part 1, we go pretty far into what is the point of what we are doing, but I don't want to repeat all of that again. Okay. So we've got, like I said, our simp program. So I'm going to stop drawing the word simp, except that I'm not. I'm going to draw the word simp down on the bottom of the screen, I think, because or maybe on the bottom, because names could be long. We want a place where we draw the name of whatever tree map node you are currently in. And then we want a region of the screen where we're going to draw the tree map. And that's just going to be some rectangle. And we're going to draw that, and then we're going to be happy, right? So we're going to go to main. Where do we draw a simp? Here we go, draw some text. We're instead going to factor this out. We're going to say draw current tree map node, okay? Boom. Do we need any globals or anything? Yeah. Time. Let's put that up here. Current time, float 64. Okay. Boom. Hey, look, it's still exactly the same. Now, let's put this at the bottom. So, all right. I'm realizing this example program is a little bit confused. I think anyway, we'll worry about that later. So we're going to use the window width and the window height. Draw a current tree map node. Okay. Oh, wait. Oh, we're changing the color of the text. Is that real? Yeah, it's just very slow. And it's on the... Let's get rid of that. Let's have a nice violet text. Okay. And then we don't need the time. Okay, text is name of the current node, and this is not an example anymore. We're just going to draw it along the bottom of the window. Hey, check it out. We're not respecting the PlayStation title safe area. It's not a great color, is it? That's not a great color, is it? Anyway, I should have a color picker just built into everything. Okay, I guess it's the background color making it. By the way, since we're going to use colors in the tree map, we probably don't want the background to have any tint. We probably... Where do I clear the frickin' frame buffer? Or do I draw a rectangle? Clear render target. All right. We're just going to make this grayscale. That might be too bright. It's fine for now. Okay. Next, we're going to have draw a tree map. And oh, we have a screenshot. I don't think we care about that for now. Simplify that out. We could bring it back later if we want. So where do we draw the rectangle? Is it down here? There it is. Draw tree map. Okay, we should put, since draw one frame is sort of organized to be the top level thing, we'll put these both on the same side of it. Okay. So we're going to make this not be rotating anymore because that's the way we are. We're going to say x0 is window height divided by 20. x1 is, oh, sorry, window width. x1 is window width minus x0, so equal margin on each side. y0 is x0. So we're going to have like a square margin around. Hopefully this is big enough for our font that I just drew at an arbitrary size. y1 is window height minus x. We're just going to pick a nice rectangular area. All right. Okay, I literally just did the same thing here, but with b. Cosine sine theta. P0, P1, P2, P3, X1, Y0, X1, Y1. Same old, same old. Okay. So we're just going to leave the colors for now. Hey, okay. That's where our tree map's going to go. And we can, of course, change the title later on. Okay. So here's what we're going to do. We're going to have a dirty flag on here. Okay. And in fact, we're going to have a dirty flag on here, actually. We're going to init it to true. It's actually, it's here, not there. Okay. So if this, because there's another thing that we want to do that has to do with the hierarchy. And it is as follows. This is a little bit in advance, but we're going to do it right now anyway. When we go to generate the squarified tree map, the way that you do that is you want to go from the largest child to the smallest child and like pack them into the area. And that means you want this children array to be sorted, right? But we only need to do that once. So here in compute sizes, yes. So this compute sizes, we're not going to call manually. We'll just like call it when it's dirty. Right. Very simple function. Okay. And then here, you know, I mean, there we go. So we're going to add a pass 3, sort children by size. And here we're just going to go, again, over all the tree map nodes. Quick sort it.children, and we want to sort by size highest to lowest. So we're going to map each node to -x.size, right? Hopefully that works. Now the problem is we need to call, we're going to call this for a second. Oh, that's in file. Okay, so we're going to call that. We're going to say here in draw tree map, we're going to say recompute if dirty of tree map. And we're probably going to move that later, but okay. First of all, we're not returning tree map. So that's, I mean, we are, but we're not putting it somewhere. Quick sort, we gotta get that. Okay. So cool. We're not doing anything with this data yet. How to say const int, that's literally the same thing. Aren't I watching CSGO Major? I didn't know it was today. We might watch some of that today. I hope Shroud gets a lot of frags. Okay. Well, now we want to set up the display, right? So we need a Treemap display. This has never before existed. Here's what we're going to do. Let's be a little bit less computer science student, and we'll remove one allocation here. Okay. All right. So there's no reason to do that. Okay. So we're going to return this tree map now, and then in the tree map, we're going to say init tree map display. Sorry. Yeah. All right. This is going to say we have one of these. Display.treemap is treemap. And that's literally all we're going to say right now. Okay. And then we're going to recompute if dirty on the treemap display. It's going to be literally the same function. However, we're not going to do anything yet. Okay. Okay, and after we make the tree map, okay. Knew I got something wrong. Oh, well, yeah, we need to return this. Type wanted pointer to tree map. Yes, in file. All right. Visit files. Tree map display. Display. All right. Kid and display. All right. We still don't do anything different. We've just got a rectangle. Sag. Now, let's init the display. Okay. How are we going to do that? Since this isn't used yet, we're going to comment it out. Okay. We want a size here, I think. All right. Because that's how we know how to pack things. Okay, well, this is a good point. We're going to init the tree map display. And then in our main, remember how the window resizes. We got to set the display to be dirty. If we should re-init, we're resizing our fonts, and we're going Treemap display dirty is true. Okay? Dirty. It's dirty now. Okay, so when we init it, oh, wait. This is not, This doesn't take the size. You know, this thing could probably just, no check-in, just record the size. Instead of having an explicit dirty flag on this, if you just pass the size and we say, look, the size changed. Although it also becomes dirty if you modify the thing. So that's not true. I don't know. Okay, so this is going to take no. Okay, so our size is going to be x p2 minus p0, right? So we call that, and that'll do things for the screen coordinates that we're trying to deal with. Okay. So what is recompute if dirty? Well, we're going to go array resize on display dot nodes to all right, treemap dot nodes dot count. So we want this to be a parallel array with whatever's in the base tree map. Okay. Corner, you know, there's a question, let's comment this out for now. If you wanted this to generate just a series of square coordinates that you can just reissue without ever adding anything, we could keep this, but I'm not sure it's going to be helpful yet. So we resize the nodes. Now we want to pack the tree nodes. All right. How do we do that? Well, we're not doing squarified yet. So here's the thing. We know the total size. Well, if there's no nodes, there's no size, right? But if there are, then we say root size is treemap.nodes. Oh, we can't I should do subscript on the bucket array, because I want to say this, right? And I can't, because we used bucket array. This is why I'm forcing myself to use these data structures. You have to say all buckets 0 dot. The thing is, it's not that easy because element 0 could theoretically be removed. We never remove it, but it could be. So we need to figure out if subscripting really makes sense and what it does in that case. But treemap nodes, all buckets 0 size. Oh, all buckets 0 dot data 0 dot size. All right. And then we want to figure out the nodes. So we want to say for node index in treemap.nodes, and then we'll do something. Okay. Undeclared identifier, it in what? Did I mess that up? Oops. No, it's a bug. I guess. I don't want to deal with compiler bugs right now, guys. Oh, it's that. Oopsie. I told a beta user about that bug, and then I made the same bug myself. It's a bug, we'll explain it later, but it could just use a better error message. That's user error. Okay, so we're still not doing anything that changes the visuals, but we will soon. Because now, well, let's cowabunga if we get there, right? There we go. So that's great. Now, we're going to do our dumb allocation of tree map nodes. It is as follows. We're going to be having some available size that we shrink, okay? We're going to say available is size, all right? And then for each node, we're going to say area is total area, which we haven't defined yet, times the fraction, which we haven't defined yet. Total area is going to be size.x times size.y. It's just the area of that rectangle. Okay? Fraction is going to be a float of, oh, by the way, if somehow there's no size, we could figure out something non-degenerate to do, but for now, no check-in, make a root node that fills the area, right? If you somehow give me a tree map where everything is of size 0, we probably want to give you back like something as opposed to being open source and crapping out. Okay, so the fraction is going to be node.size divided by root size. All right? And we're going to cast that to float. Now, so the area is the total area times this. Okay. And then we're going to redivide. This is stupid because we just multiplied by size.x and size.y, but now we're going to say width is area divided by size.y. Now, the reason we're doing this is because later we're going to have a different strategy for figuring out the rectangle. But right now, we're just going to say width is area divided by size.y, and height is going to be, size.y, right? So width times height is obviously area, okay? And then we're going to say available, we need a corner that's going to start at 0. Okay. And we're going to say available.x minus equals width and corner.x plus equals width. And oh yeah, the display node does need a corner, right? Okay. So let's do this. dn is display.nodes sub index. All right. So again, this tree map has this tree map has some nodes in some order. And then this array is going to be parallel to that, right? Let's even write that. Parallel to treemap.nodes when not dirty. Okay. When treemap display is not dirty. So we take this display node, let's say call it D, and we're just going to say d.corner is corner and d.size is width height. Okay. So this is going to give us a really horrible tree map. Okay, now I just realized I did the wrong thing. This is not right. Because we're just allocating little strips from some global thing. That's not what we want to do because this is hierarchical, right? And so what we really want to do is if the index is 0, all right, I might just delete literally all this code. Let's see. So if index is 0, well, actually, right, we could put this in here and we can get rid of our no check-in. We don't want to divide by 0 later. Okay. We're going to get this display node at the top here. We're going to say d.corner is the corner. d.size is size. Let's call this outer size, right? Or something. It's like outer wilds. Okay, this available is not even a thing. This corner is not even a thing. Because again, okay. So we're just setting that to the corner and the size. Now, if we're not node 0, okay, I keep screwing up and thinking about this wrong, because I was like, then we'll visit the children instead and we'll allocate from the children. But that's not, you actually do want to go from the root down, like I literally did. So we don't actually want this to be a for loop, actually. Let's be a computer science student and make it a recursive function. Because you want to go visit the children in like tree. We went through all the trouble of sorting the children and all that. All right. So here's what we're going to do. We're going to say allocate. Allocate makes you think of memory allocation. Size nodes. We want a pointer to the root node. So I'm retyping literally this. All right. So we get a pointer to the root node. Let's set this on the root node no matter what. And then if we recurse, it's actually fine because we'll divide 0 by the size, so we won't be dividing by 0. So this actually is going to be okay. So now we're going to say allocate or size display node size children, right, for the root and so we don't, the annoying thing is right now we're not storing the index on the Treemap node, which we need to get to the display node. So we're going to have to put that. We're going to pretend like we have it. So we're going to size the children by the root and the Treemap display. All right. Do we need anything else? I don't think so. Let's just see what happens. All right. So size children is going to go root Treemap node, and display is Treemap display. All right. Like I said, we don't have the index, but we're going to say for root.children. Okay, this is the for loop that we want. And this is we don't have that index yet. We're going to have to add it. Now we get the display node, and now we're going to do some of this stuff. So let me just choppy pasta this. So the fraction is going to be child.size, right? Okay, so root size is going to be root.size dot, actually, right, okay. I do have to avoid a divide by 0. I don't know. Okay, so we take this fraction. The area is going to be root area, right? Root area is going to be we need the display node. Root display is display.nodes, root.index. We also don't have that. It's the same index as this one. We don't have it. So root area is going to be root display.size.x times root display displappy. I typed displappy twice. What is wrong with me? .y. Okay. So we've got an area. We've got a lot of misspelled things. We take the fraction, okay, we take the root area, we take the width. Again, we're chopping off rectangles in a suboptimal way. So our corner is going to be the same. It's going to be root.corner. No. Actually, we're going to say corner is root.corner. We're going to start at the corner, and we're going to move this as we go. So we pick the corner, we pick the size, and then we don't need this available, and we just move the corner along, okay? I'm sure people are totally lost at this point, but it's something like this. Now we need this index. Okay. Wait, we have the locator. I mean, yeah. Okay, so get index is going to be an inline convert a bucket locator to an integer index, right, which is just, right, so you can see the locator. We're going to have result bucket index times node dot we can't get to the array from the node, so we need this times treemap.nodes.items per bucket. Actually, I don't think we need this cast because that'll upconvert. So we take the bucket index, we multiply by the items per bucket, and we add the slot index. That's it. Return result. So we need to get index. Treemap child. Okay, it's fine. Treemap root. Now, size children is not recursive yet. Okay. So we could do that. Here we can just go size children treemap child display. Displappy. Why does my brain type displappy? I don't get it. Okay, I'm sure I made a ton of mistakes because I changed 3 times the basic structure of what I was writing there. I apologize for that. I'm sure that was very okay. So this isn't right. See, we want display root display dot node sub 0. This is display root. All right. Okay. Treemap node, that's spelled wrong. Root display.y, that's not a thing. Root.corner. This is root display dot corner. Size.ny. I don't even know. We love New York. 152. Bucket index. Let's just do this. Type mismatch. Left type U32. All right. Oh, that's an S32. That's why it doesn't convert. All right. Ooh, so many mistakes. 138. This just happens once things go to a certain size for me. Is like, okay, we're just doing the, okay. So size. Display. I don't know what's going on with my brain and display. Tree map. Bro, okay. Now we're still not drawing anything. But in principle now we could. Okay. Now, here's the thing. We have all these rectangles. If we draw them all, we're going to be drawing a bunch of rectangles on top of rectangles on top of rectangles. And we're going to redraw the same pixels many times. But we could change that later, right? Like if it's a non-root node, we could change it so that we only draw the outline of the node or whatever. Like we're going to have to figure out how much we want to draw for non-root nodes. Most of what we want, or sorry, non-leaf nodes. Most of what we want is actually the leaf nodes. I do think we're going to want in here, node is a tree map node, and we're going to set this. Okay. These variable names I don't think are the best. I don't like the word root display. But we don't have a better term for that yet. We might land on that later. Root, sorry, I got this backwards. Root display dot node equals root. My brain is a little bit fried. Let's take like a 2-minute break. Did I figure out how to build LLVM on Ubuntu? No, I would never want to do this such a thing. Yeah, we might have to chai up here in a bit. We might have to chai up. Okay. So we could just print in ASCII the rectangles because they're probably wrong. But would we tell if they were wrong? I don't know. Let's just draw them and then we'll find out that they're wrong. So actually we could just print, actually, I mean, we could just do this. Print display tree map display. That's going to show us a lot, I think. I don't know if we'll, yeah, okay. It's not super intelligible. because we're not drawing the names of the fields. Treemap node index. Right. I don't know why. I guess I put that there. We don't need that. We just have the pointer. So we'll get rid of that. 1503, that looks like a reasonable screen coordinate. These are very thin frickin' rectangles sometimes. We're going from 0 to 888, which seems wrong. This y coordinate, not good. So let's see about that. Oh, because we're not, right, we're not adding. So the y coordinate being 0 is correct. Let's redo that without the zeros in them. Hey, look at all these numbers. It's actually not as ridiculous of an amount of text as I would have expected. Okay, so corner size. So it goes out to 1500 and something. I mean, it seems pretty reasonable. Let's just draw it. All right. Here's what we're going to do. We're going to go for, let's comment this out in case we want the reassuringness of a solid rectangle back. We're going to go for node treemap display in nodes. All right. And we're going to say P0 is, let's have our corner. This is our screen corner, which is not included in the tree map coordinates. So P0 is going to be corner plus node.corner. P1 is corner. I don't know, something like that. Okay. This is what we expected roughly because, again, we have a very stupid allocation strategy that never does anything in Y. It's literally just packing in X. And that's fine, maybe. So I think the next thing is to detect when the mouse is over a thing, and we'll set the current node, right? We'll set the current node. All right, that worked better than I expected. So current node is null. This is going to be and then if And then we say current node equals node. Okay, this is a display node. Okay, well, what are CX and CY? We need to figure this out. So, is this in... Do we get the cursor position? All right. Get mouse pointer position in window creation. Okay. Okay. Mouse X, mouse Y, R. I think my window. All right. And then down here, we're going to convert these to floats. Okay. So right-handed. Okay, we didn't pass right-handed. And maybe we don't need to pass our own window. We want right-handed, even though that drives everybody crazy. Vector 4, oh, I said C1. Whoa, I was like, what happened? All right, so now maybe we're setting the current node. All right, so if no current node return, we're just not going to draw anything. Otherwise, text is current node.node.name. All right. Hey, that didn't work. Why didn't it work? What is going on? We are calling it after. Maybe we're not setting the name. I'm going to make this easier to debug. This means that once we get one, we won't unget it, right? Okay, so I'm probably doing a stupid thing with the mouse coordinates being wrong, right? Something. So do I want to pop open the debugger, or do I just want to look at it for a second? I mean, let's just do this. Probably my cursor positions are wrong for some reason. Oh, guys, this should be P3. Still not working. Okay. It should be P2, not P3. Guys, what is my problem? Hey, look, it works when you put the right point in. We don't need our print statement that I typed twice. So here we go. So this is all the files, all the files. Okay, well, now we get to the part where we actually try to make this a good shape. And making it a good shape, I think, is going to require us to change our recursion strategy, okay? Because as I recall from the paper, what they do is they just say, okay, we'll pick a rectangle for the current node, and then for the next one, we see, should we pack it vertically, actually use our y coordinate, imagine that, pack it vertically alongside the old node, or do we like put it out here in a new column, right? And, or something like that. And the decision for that is based on the aspect ratio that you're going to get if you do either of those things, right? So the thing about that is you, of course, need to allocate all of the nodes at a given level before you go down into the children, because you're changing the shape at that level. Right? So, and you know, if you change the shape at that level, it changes the results for the children. So we actually need to change, before we even actually start using our y coordinate, we want to change dude, I didn't get quite enough sleep last night, so my brain is just a little tired. So, okay, I'm just trying to think of the file. So we're going back to the Treemap file here. And when we init the display, we size the children. Okay, so we're going to do this children thing in a 2-pass. Okay. It's going to be 1 pass to do almost everything, and then another pass to just do this part. And the reason is because the algorithm for this is going to resize other children or something, right? We're going to look at that in a bit. But anyway, so we figure out the sizes of all the children of the current node together in harmony. And then we recurse, right? So yeah, same result. No big, same result. Okay. Now, we need to, let's think about, we're probably going to pop open the paper and recheck what they say about this. Even though it's relatively simple, there might be some nuances. So this computation that we're doing right now is fine for the first guy, right? Because even if there's only one child, even this fraction will be 1, right? And then the area will be root area, and then we'll just get size back here, right, for width and height. And we'll match the size, of course, maybe with a little bit of numerical error. So that part's fine. And then if it's not fine, we want to say there's some nodes in our current column. Okay. There's some nodes in our current column. And when we add, so in principle, the current column is just sort of like a bigger rectangle, right? And we care about the aspect ratio of that rectangle. And what's going to be more square? Is it going to be more square if we put the next guy into our same rectangle? Or is it going to be more square if we start a new column? Although those things, right, it's not, so the area will be as square either way, I guess. The question is, how square will the new rectangle be? Is that it? How square will the new rectangle be? By the way, you measure how square something is by, you know, is the width over height close to 1, for example. Right, the closer to 1 you get, the more square you are. So, yeah, I believe we want to do something like just keeping a notion of what's in the current column. And we say, now it's weird because you do end up changing the shape of the previous guys that you already made decisions about. But I think if I recall correctly, the paper just sort of says, yeah, but you know it's fine, right? It's one of those situations where it's like, you know, you could do some NP complete crazy search, but we don't do that and the results are fine, is I'm pretty sure what it says. Let's just take a look at the paper. Because I didn't get quite enough sleep, I think this isn't going to be a mega long stream. We've already got stuff on the screen, which is great. And now it's just a matter of making it there. Well, not just. There's many things to do. But the next step is just making it the reasonable shape that we would like, right? So let's look up the paper. Squarified tree maps. I don't know. Does anyone know if there's a better paper than this one? This might be the original one. So we're not even doing a tree map yet. We're literally just going in a line. So we might want to figure out how did a traditional tree map do it? Because that would be maybe a good next step, right? So here they have this A16, which I guess is this whole rectangle. And then they have B3, which is not labeled, I guess. That's this. And then E1, F2, vertically. And then C3, and then D10, which is G2, H4. Do they just alternate between horizontal and vertical? Is that what this is doing? Because that would be pretty easy to implement. Each node is associated size of leaves. Tree maps recursive subdivision. First horizontally, next vertically. Yeah, let's do that. Let's do that. That'll be a good learning step, right? That's not the final thing. Okay. Well, you need to know the depth of the node, and we can just do that. All right. And there we go. Okay. Now, here's what we're going to do. All this is the same. This is the same. If depth and 1, we do something else. We do exactly what we were already doing. All right. Here, we do height is area divided by size dot x, and width is size dot x, right? And then, okay, that's the same. Oh, except I don't know. And then corner dot y plus equals height. I didn't think about that like at all, but there we go. I mean, these results aren't great, but like you can already see how this is kind of useful. The thing is, yeah, I mean, judging the size of these long, slim dudes is not that easy. right? And this gets kind of gnarly out here. But it's way better than what we just had. The paths changing so fast gives nausea. Sorry, we're not as slow as a Windows Microsoft program. I mean, would you rather have us delay for 3 seconds after you move the cursor before we tell you the thing? Okay. So here's traditional Treemap. Okay, so figure 2B shows an artificial organization chart modeled after the structure of our university. Why is that artificial? 6 levels in the hierarchy are shown. The final 30, 60 triangles, rectangles denote individual employees. Yeah. Yep. Thin elongated rectangles. That's exactly what we were just seeing. All children on a level are treated the same, hence the presentation of a small file is degraded compared to its larger siblings. Squarification. How can we tessellate a rectangle recursively into rectangles such that their aspect ratios approach 1 as close as possible? The number of all possible tessellations is very large. It's NP hard. However, for our application, we do not need the optimal solution. A good solution is required. Yep. Empirically. I love how much work this word empirically in parentheses is doing, right? First, we do not consider the subdivision for all levels simultaneously. We produce square-like rectangles for a set of siblings. Yep, that's what I thought. And apply the same method recursively. We replace the straightforward subdivision process for a set of siblings technique by a process is similar. Okay. Width 6 and height 4. Standard gives us this, blam or blam. That's fine. Let me open this window for a second. The first step of our algorithm is split the initial rectangle. Okay. We next fill the left half. Well, by half, I think half is an approximate word there, right? Then we add a second rectangle above the first. The aspect ratios improve. I see. So by half, they mean it's divided into two regions. Okay. And then when you that's similar to what I mean, when I was saying continue the column, that's sort of the same thing that they're saying as with halves here, I think. Start to fill the top right partition. Yep. So here they reject the 4, I guess. So 3 over 2 is 1.5. 4 over, oh, this is the, okay. This is the first thing that's clarified. We're talking about the aspect ratio of the unused region. Of the unused region. Of the onion region. All right? It would have helped if they had drawn a little bit more here, but okay. Although, these numbers don't totally make sense at all. So first of all, when they go 3 over 2, that looks like, and 4 over 1, that looks like vertical over horizontal. But how is this 8 over 3? That's wrong. How is that 8 over 3, guys? If this is 3 over 2, this must be the 3 and that's the 2. And this must be the 4 and that's the 1. Although this is not to scale because that's not frickin' 4 times the thing. The aspect ratio of the bold rectangle. Okay, no, you're right. That makes sense. That's why it's... See, I'm tired, guys. Okay. Okay, never mind. I thought it was this part. It's not. It's this part. Okay, 8 over 3. So 8 is vertical, 3 is horizontal. No, see, even that doesn't make sense. They're not consistent about this. That's what's so confusing. I mean, it kind of doesn't matter, right? Because if you want to know, okay, they are drawing aspect ratio so that the higher number is in the numerator. That's what they're doing. Which I guess is fine because it's symmetric in the sense that you want the thing closest to a square. And I guess this makes it easier to ask which one is closer to 1. If the denominator is higher, you just flip them, right? And then you say, is it closer to 1 than the previous? Which is just a less than comparison at that point, right? You don't have to do anything funny because if the numerator is always higher, then the number is decreasing as you get closer to 1. So that's actually cool. I dig it. They had the definition 2-page. Yeah, I don't read things very carefully. This is max height, width, height. That's just a kind of phrase that I just skim over, right? Okay. So this is what we do is we say, what would it be? And then we switch to horizontal in the next part. And then we switch to vertical and then we switch to horizontal. And this is all siblings within the same level. All right. Now this is a little bit tricky because there's some if statements here, right? The direction you're going depends on the starting aspect ratio. Okay, so let's keep this nice loop commented out. Because I'm tired, we're just going to start typing this, and we may not even finish, right? Okay, so for this aspect, for determining vertical or horizontal, we want to say root aspect is okay, hold on. Active, we're going to say active size. No. We're just going to say corner in size. And then we're going to say aspect is size.x divided by size.y. And we're going to say horizontal is aspect is greater than or equal to 1. All right? Here, and then if we decide to switch directions, we'll change these things. Except this aspect is like, no, you know, we just need to change horizontal or not. Okay? So we're going to get the fraction. And we're going to get the area. And we're going to say, I don't know, if horizontal, we're going to do something, else we're going to do something else. Wait. By horizontal, maybe I should say call that vertical, because we're laying out vertically. Right? Laying out vertically. Also, I mean, the weird thing is, for the first one, it simply doesn't. Oh, yeah, it does. Okay, never mind. Yeah. No, wait. Horizontal does mean, this is confusing. Horizontal means we're filling, the column is filling horizontally, but we segment it vertically, okay? Okay. Do we need to do something special for the first one, right? I mean, it kind of seems like we do, because there's nothing to compare against, right? Okay, this might come out more complicated than it needs to be. So we're gonna say if first, All right. We basically do this, right? If we're horizontal, we do that. Otherwise, we do this. But we're going to say free I don't know. This is the region that we're not using, right? If first equals false, free corner plus equals width, free size dot x minus equals width, free corner plus equals height, free size minus equals height, right? So we've got a fill region and a free region, and we're doing this, okay? And then we're going to reset the size of the fill region. Okay, to width comma height. Okay. And then I guess we continue so that we don't have to put an else. Okay, now here's what we're going to do is we're going to say aspect is, and we're going to use their min max. We don't need this. We're going to call this fill aspect. It's like fill fish, but an aspect ratio. And then down here, we're going to do aspect for this is max. Use their interesting definition of this. This is the branch free, as long as nothing was 0. So we take that aspect. This is old aspect. Okay? And then we're going to say there's some new aspect, and we're going to say if new aspect is greater than old aspect, we don't like this shape. I kind of want to go to. Bruh. I kind of want a go-to. And I'm not trolling right now. And we don't have go-to yet in this programming language. Time to add go-to. Well, we're not going to rat hole to add go-to. Okay, so if the new aspect is big, we don't like this shape. And then we're going to say, we're going to do some stuff. Like we're going to say horizontal is not horizontal. We're going to say corner is free corner. Size is free size. Okay. because we're moving over. Actually, we don't really need to go to here. Here's what we're going to do. If not first, okay. We're going to do this, and then we're going to say first is true, else we like this shape. We're going to do something there, right? We need to resize. This is the thing, is we need to resize all the dudes, which kind of sucks. We could avoid the noid, right? Total in group. Fill. See, we're using the word size for two different things, right? We're using it for the size on the node, which is a scalar. We're also using it for the display size, and those things are related, but it's confusing. So I'm going to say weight. We might change the other thing to be weight, just to give us a different clarity. Or we might call size something else. Okay, so if we're first, then fill weight total plus equals area. No. Child.size. See, this is screen area, etc. Fill weight total. Okay, now we're going to do some stuff and then continue, which then means we don't need to check if first. Okay, because we know that's true. Go, you know it's true. My soda's flat. That's the thing about these Waterloos. The sody pop is flat after 45 minutes. It's like if you had a soda stream. Okay. So there's a few holes in what we're doing. First, we don't compute new aspect. That's not a thing. Okay, so new aspect is going to be if this is first, we don't need to plus equals this. Okay? Fill weight total plus child.size. All right? If we accept it, we set that. Okay. New aspect is going to be see, what we want to do actually is factor this into a function, right? Although it's kind of a trivial function, but new width, new height is get rect. Horizontal size. It's like not worth making it a function, honestly. Also, we didn't declare width and height. I guess I deleted that. Let's just do this, make it easier to read, and okay. So we're just going to copy schmasta this, but not all of it. We're going to go here. We're going to go new width, new height, and new Vegas. Fallout, new Vegas. Okay. Area is root area times fraction. That's not right anymore. Let's imagine that it's right. Okay. Okay, anyway, once we have this new aspect is max, new width over new height over new width, okay. If we didn't like that, we do some stuff. Okay. Area here so this root size is not okay. So this, right, was really, if we move it down, we get this local variable size, and this is something that we're changing through the loop. So we're just going to say active area. I don't know. That's a weird bringing the word active into it. And fraction, we're going to have area is just Going to move this up here. We've got our new fill weight, and then new fill weight divided by root size. And the area is going to be the active area times fraction. Okay, this is fine now. Our no check-in goes away. Did I delete root size? Okay, it's fine, 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 fine. So we add things to the single bopper. Okay. And too tired to be doing this, but okay. So yeah, so we're growing this rectangle. You know, we don't actually need to resize the dudes yet. We don't need to individually size the dudes until we're done. And switch. Right, so that is a thing that we need to do. We're going to want to save the index of where we started. So basically, once we decide to bag it and switch what direction we're going, then we know the width or the height, and we can just size everybody. So up here, we're just going to say unsized cursor is 0. Size the dudes from unsized cursor to it index -1. And then let's actually go for I unsized cursor to it index -1. No check-in, size the dudes. And then we swap a Rooney. We set the active region to be the free region. We might change corner and size to be active corner, active size. I don't know. And then we say first, right? And oh, we have to say unsized cursor is it index. Is it called it index? Let's call it child index. This is turning into quite a long loop. Quite a long loop. So this is going to be like this. Okay, if we're horizontal, the width of each thing is going to be right? Because if we're horizontal, we're actually going up, right? We don't have the area of the sky. C area divided by C dot size dot X, right? Okay. And then cursor dot X plus equals C dot size dot X, cursor dot Y. This is, more code than I wish it were. I could probably figure out a way to shrimp it. Shrimply Shrimpleton. Okay, we need C area. That's something. This cursor is out here. C dot corner is corner cursor. Okay, C area. This is the relative area, right? So this is C dot size divided by, no, this is C dot node dot size divided by the new fill weight. Wait, this isn't a display node. It's a Treemap node, right? So it's C dot size divided by fill weight total. Okay, times area. Okay, there's going to be so many mistakes in this, guys. Okay, we don't need to resize all the dudes because we're sizing them in the end. We could actually set the width or the height down here and not do it here, but I don't see the point in that. Okay. So I mean, this seems, am I forgetting any major part of the code here? It seems roughly like the thing. Like I said, I'm sure I've made 17 mistakes. Does this make sense to people? Mistake number 1. What's it called? Root.children. We got pretty far down before our first undeclared identifier. C.corner. That's because we want the display node. Okay. These are all D. Width is not a member of vector 2. Loss of information. Okay. This is unlikely to work. Will the whole map be recomputed as new data comes in? Well, the visual part of it, yeah, you would have to recompute probably. I mean, I don't know how you would know. Oh, this is going to be gross. Well, that's unexpected. Remember, the background is grayscale, so the only way to get red is to draw something so incredibly huge that you cannot see the gradient. Right? So we goofed, by which I mean me. I'm just going to step through it. You know, sometimes I don't want to step through it, but sometimes I do. We're just going to do that. Yay. Treemap. Okay. Shut up. Of course projects are loaded and ready to use. What? Like, isn't that insane that they have to do a pop-up now? Because the expectation is that it might be so slow to load your project files that they wouldn't be ready to use for a long time. Project files, which, by the way, just say what the source code is. That's all they do. The project files should be way smaller than the actual source code. And yet the geniuses at Microsoft, yeah. What file was I looking in? That window distracted me. Treemap. Like, I'm using a frickin' giant supercomputer here. And we might not be able to load the project file for an hour. Okay. Size children. Won't someone think of the children? Okay. Okay. This root size, I don't think we're using. Oh. Okay, that's wrong. When things are wrong, let's fix them before stepping through. This active area. Okay, this is the wrong thing. This is the wrong thing. See, this should be this. Okay. All right. That was our very nice loop that worked before that we didn't check in, that we should have checked in. All right. Well, it's something. It's not correct, but it's at least not sausage dog tends to infinity anymore. Now we have a rectangle. It looks like we're not correctly incrementing to the inactive region. Let's step through it now. Okay, corner, size, fill aspect, horizontal, true, that's all correct, I believe. This free corner isn't, yeah, that doesn't need to be up there, right? Does it? Maybe it does. Anyway, let's just see. All right, so we get the display node, we get the new fill weight. Are we using that? Yeah, we're, okay. Okay, that looks correct. Active area is going to be around 1 million, a little less, a little more than 1 million, by which I mean. Fraction, less than 1 for sure. Yep. Okay, so I wish we could see it. So area is active area times fraction. No problem. No problem. Okay, so we are first. It's like when somebody says first on the forum or on the YouTube comments. Fill weight total is child size. Width, height. All right, so width, height. Yeah. Free corner gets offset to the right. Okay, this seems fine. And the size of the fill region is now width, comma, height. Okay, great. And corner is still 0, 0. That's great. Totally fine so far, unless I've spaced and missed something. Now, we're seeing these same variables, fraction 0.42. Okay, so this is getting bigger, and we're fitting into the same width, okay? That's the important part. So active area got smaller, though. It's important to remember because The goal of the first iteration is to shrink our region. Active area used to be the whole thing. Now it's we chopped a chop. Okay. So old aspect should still be should be equal to, wait. Why is that not? Wait, is fill aspect? We don't really need that variable. That's a stale variable that we're going to delete. That was only used for the initial decision. Okay. New width, new height. If horizontal, okay. New is new width. Okay, no, this is wrong. This is backwards. Horizontal actually means here we're laying out vertically, right? That's the whole confusing thing. So it really should be the opposite. So we'll fix that. And then it still won't work. Well, it might, but probably not. Now we have literally nothing. At least before we had things on the screen. All right. Okay. Active area, we're not first. Old aspect is 228. That's not a very good aspect ratio. New width, new height. Okay, new aspect. 103. Wow, that's a much better aspect ratio for if new aspect is greater than old aspect, nope. Instead, we go fill weight total. This is quite yeah. Yeah. Okay, so now here's the thing. Oh, our sizing step must be busted, right? Because we haven't assigned, I was like, oh, all this seems right, but we have not assigned to the sizes of these dudes yet. Okay, so now we actually, our active area could be moved out of the loop, I think. Anyway, fraction area old aspect. Whoa! Okay, old aspect is busted. Old aspect is busted because that's just staying the aspect of the root region. So this is going to cause us to think that we're better when we're not. All right. So we're going to be like old aspect. Okay. New aspect is going to be a thing. If we don't like the shape, then we're going to set old aspect because we just changed size. All right. Otherwise, we're going to say old aspect is new aspect. Right? That seems to be the thing. Okay, now we're back to our same not looking good. Okay, so now old aspect 194. Oh, we actually need to set it down here actually. Still probably not going to change much, but there we go. And that means we'll just leave this initialization, but it actually gets iterated the first time around the loop, so we could leave that uninitialized. So, okay, that looks a little better, I guess. Except here's a really long, thin guy that's like overlapping thing. That's not supposed to be able to happen. So there's clearly some issues. All right, so old aspect 228. All right. New aspect 103. Great. Old aspect is now 103. Now we're trying to bump it up to 124. We do not like that. We do not want to go up to 124. Okay. So now we're going to size the dudes. Corner cursor. Oh. Wait, no. This should, okay. So fill weight total is this. And we should be iterating 0 to 1. That's true. Okay. This should be about half of fill weight total. Yeah. Okay. So we have area, we have C area, which should be about half of that. It is. Okay. Corner cursor. I feel like we're just not setting corner correctly. Right? Because here, well, let's just see. We're doing horizontal, so (256 pixels. Maybe. I mean, I guess that's plausible. Yeah, that adds up to about 512. No, this is wrong. Okay. The reason we know this is wrong is because our original size, right, is 800. We only filled half of that, and this loop is supposed to fill the whole thing. Okay. Oh, okay. No. No, 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 no. This area variable is not right. I don't think we use that for anything. So this area variable, oh no, we do use it down here. This is active area. At least. May not be the only problem, but again, we're figuring it out. Oh, oh. This is, I think, also active area. Could be either, honestly, but... Hey, we're back to this. Isn't it great how we like toggle back and forth? Isn't that great? Shut up! You can't see that probably. Windows wants me to update or finish installing, or just leave me alone. I'm trying to find the bugs. I'm trying to find the bugs. Okay. Active area. I mean, really, there's no reason to, it's error prone to have that in a variable. But all right, let's just step through it again. Old aspect, new aspect. Oh boy, okay, that's really wrong. Our new aspect is horrible. So the new fill weight divided by the root weight we don't want that. We don't care about the root weight here, right? We care, this fraction is wrong. We care about, right here, we want to know the child size divided by new fill weight. I don't know. Right? So, because this is the fraction of the active region that we're filling in. Okay, and then active area times that fraction. Dude, my brain's too tired to do this right now. Obviously, as you can see from the results. I really messed something up there. Okay, so active area, fraction, area, new aspect is still F'd. What's going on? Active area times fraction. What's fraction? It's 0.4. That's fine. Active area. Oh, this is... Wait, what? Okay, let's delete some things. New width should be size.x. Okay, that's wrong. Okay, we goofed. I kind of went backwards somehow. We goofed on the initial iteration. We're supposed to have picked a much narrower size. See, size.x starts here. And then here we go, fill weight total. Active area. Okay, this is the problem. This is where, okay, so this is supposed to be what we, okay, yeah. What we need is the fraction of the root weight times size.x, honestly, because it's a one-dimensional proportion. So I don't know why I'm even finding the area, right? Okay. Okay, guys, I'm sorry. This is what happens when I'm this tired. It's a disaster. Although we're actually doing fine. So we get this fraction. Width equals fraction times size.x, right? And height equals fraction times size.y. I think. Hey, that looks kind of better. I don't know why. I feel like things toward the root should be on the left, but we've got this. Oh, this is, okay. So somehow we're still, our free region still isn't the right size. So this is, remember how I said we're drawing things on top of each other? This is like underneath, and then we're putting stuff on top. So this is better. This is better. But as you can see, there's a problem of some kind. I kind of don't. These are kind of weird results, but maybe it's fine. Oh, it looks weird. Okay. It looks weird because, again, we're seeing things that are not leaves all over the place. So we're still not filling out the total area. Not by a long shot. So we're sort of skirting along. Dude, this should be actually pretty simple. So we just have to figure out what Chunky's deal is. Okay. Okay, so this active area variable, we're not So the fraction here is out of the new fill weight. This is very weird because we're sort of doing the same thing transposed in these, I don't know. We'll try to factor it later. The active area is size.x times size.y. Area is that times fraction. That looks okay. Although, again, we don't need to do this whole area thing here. This is not necessary, all right? So new height is fraction times size.y, fraction times size.x. All right, we don't need this, which means, which means we don't even need that either. That's great. Get rid of variable, well, hold on. We were using active area down. Yeah, that could be what's wrong though. Let's get rid of that. Let's move this down to here. I don't know. I mean, again, we're doing the same thing here. We don't need the area here, right? Here we just need fraction is the size divided by the fill weight total, right? Size of the child divided by fill weight total, which should be the sum of all of these. And then we set the corner, and then fraction times size.y. Okay. I don't feel like we fixed anything fundamental here. If something's wrong, though, it's probably this. Like fill weight total isn't, for some reason, what we thought. Although we could recompute it here, but we shouldn't have to. All right. Oh, yeah. Line 181. That is what we do, yeah. Why don't we have to do that down? Oh, because our fraction is casted to a float. Let's do that. Same result. That's, like I said, I didn't feel like we were fixing anything, but we did remove cruft and clean it up. So let's just check that loop again, because I feel like we're just not going all the way. Okay. So child index is going to be 2, right? Yeah. So fill weight total. Okay, so fraction is around 0.44, 0.53. Oh yeah, the first one's bigger because it's sorted. So x d.size.y corner cursor.y. So size.y is 888. So corner cursor now should be about half of that. 470. That's good. Okay. 888. That's good. So we filled it vertically. Okay. We filled it vertically. Corner is free corner, right? So yep, so size goes, free corner starts there, free size, that all looks fine. Old aspect. Doesn't matter because first is true. We actually could delete this line as well because we're not going to use that. Why do we have root weight here? Why do we have fraction? Oh wait, we fell through down here. Oh, never mind. I thought we were at the top. Okay. So fraction. Okay, is this right? No. No. Because okay, here's the thing. We've got our free region. The free region represents how much of the weight is remaining. But we're dividing by the total weight, including the guys we already allocated. Okay? All right. We have to subtract off so yeah, remaining weight is root.size, all right? And then as we go through here, once we decide that we like these guys, we say remaining weight minus equals c dot size. Okay. Oh, also, we don't need that. Hey! Looks right to me. These are all leaves. Well, no, that's not. Maybe. Okay, this is still, I think, not right. But we're closer. We're closer. We shouldn't see non-leaves at all, but we are in some cases. So we're still goofing. If this was open source, though, we'd ship it and say it's done. It's not quite done. There's still a mistake. But this is a good, because I'm super tired, like, it's just, we're making more bugs than we would if I were not super tired. So we're going to take a break, but then we're going to come back to this later on and figure out what's happening. It's still, you can still sort of see, we're kind of doing the same problem. It's just less severe. Like you could see here, here's a non-leaf, and it's this rectangle, and it's getting filled up by these leaves, but we're just not getting the whole area for some reason. It's probably a relatively trivial mistake that we will pick up in part 3. So what will part 3 be? Part 3 will be we would like to fix this bug, of course, and then I think we want to be able to pan and zoom around the view. And then maybe have colors or something. I don't know. We'll figure out some better way to shade the squares. Yeah, see this? It's the full area is not, the full Monty is not being used. Part 3 later today or tomorrow? Probably later today. Yeah, so by the end of part 3, we want to just have a correctly viewed thing that we can pan and zoom around, and then for part 4, we could actually retarget this to program visualization instead of file tree. Maybe that's how we'll do it. All right, thanks everybody. We'll be back on later on. Some rectangles don't even have green corners. Yeah, that's because, so what's happening is we fill from Y0 upward. So the green corner of like this guy is down here, and we covered it up with littler guys. The thing is, he should be totally covered up, but he ain't. He ain't. I think it has to do with the remaining weight. Because if you look here, like, we're filled to the top, and then we switch to sideways, I don't know. So one thing that you could think about is, hey, maybe we want to be able to view the hierarchy. Like, you could have a hierarchy select where it's like, okay, we're at level 0. Mouse wheel to go down and up or something. And then you could act, like right now I can't quite tell where the, like this is several levels deep, right? So like checking the top level nodes to see what they are would be useful. We could just have a little toggler button about which mode you want to be in. Leaf mode or hierarchy mode. Highlight the parent nodes with a border. You could, I just think that doesn't help a lot of the time. Sometimes it does. Sometimes it doesn't. Maybe we'll do that instead of retargeting the program later today. I don't know. All right. Thanks, everybody. We'll be back on later on.